10 days before the rest of the world even knew a genuine interstellar object was heading toward us, one telescope had already photographed it, quietly, without realizing what it had found. That telescope is the Vera C Rubin Observatory, perched high at the summit of Cerro Pachon in the rugged Chilean Andes, and the story of how it quietly beat every other instrument on the planet to the discovery of humanity's third confirmed visitor from another star system is one of the strangest cases of cosmic timing in modern astronomy. It's a story about a machine so powerful it accidentally photographed history before history had officially happened, and about a determined team of scientists who had to go back months later and dig carefully through the archives to realize what they'd actually caught on camera. Here's exactly how it all unfolded, step by step. On July 1st, 2025, the Atlas Survey, the Asteroid Terrestrial Impact Last Alert System, a network of telescopes built specifically to hunt for objects that might one day threaten Earth, flagged a fast-moving point of light near Rio Hurtado, Chile. Within a single day, the International Astronomical Union's Minor Planet Center had confirmed what many astronomers already suspected, the moment they carefully plotted its unusual trajectory. This wasn't a normal asteroid or comet native to our own solar system. It was moving on a hyperbolic path, arriving from interstellar space, and it would become known as 3I Atlas, the third confirmed interstellar object in recorded human history, following Oumuamua in 2017 and Borisov in 2019. Telescopes around the world scrambled to turn their instruments toward it. But months later, a team of astronomers led by Colin Orion Chandler decided to check something. The Vera Rubin Observatory, one of the most anticipated telescopes ever built, had been in the middle of its commissioning phase throughout 2025, a critical testing period during which engineers and scientists fine-tune the instruments, calibrate the cameras, and validate that everything is working exactly as designed before the observatory's real, decade-long survey officially begins. During that commissioning phase, Rubin had been taking test images of the sky, essentially practicing, pointing its enormous camera at various patches of space to make sure everything functioned correctly. So the team went digging, they pulled up Rubin's commissioning data, and searched for any frame that happened to overlap with the patch of sky where 3I Atlas would have been, going back before its official July 1st discovery date. And there it was. Not once, not twice. Rubin had serendipitously captured 3I Atlas 9 separate times between June 21st and July 2nd, 2025, up to 10 days, before the Atlas survey ever flagged it, and before anyone on Earth knew an interstellar visitor was even in our skies. The observatory had photographed the discovery of the decade purely by accident, simply because it happened to be testing its camera on the right patch of sky at the right moment, completely unaware of what was drifting through its field of view. To put that in perspective, you have to understand just how staggering the Vera Rubin Observatory actually is as a piece of engineering. It houses an 8.4-meter telescope, paired with the largest camera ever built for astrophysics, a digital sensor roughly the size of a small car, capable of capturing images so detailed and so wide that a single photograph can contain 10 million galaxies. It was originally conceived back in the mid-1990s, under a very different name, the Dark Matter Telescope, before evolving into what it is today, the centerpiece of the Legacy Survey of Space and Time, an ambitious 10-year project designed to photograph the entire visible southern sky over and over again, cataloging every single change, every flicker, every faint moving object, building what will eventually become the most complete motion picture of the universe ever assembled. When Rubin released its first debut images back in June of 2025, the results were staggering even by the standards of modern astronomy. In just a few nights of test observations, the observatory had already revealed more than 10 million previously unseen galaxies clustered around the Virgo cluster, along with roughly 2,000 previously undiscovered asteroids, spotted almost as an afterthought during what was supposed to be routine calibration. This is a telescope so sensitive that it can see roughly 100 times fainter than most other sky surveys currently in operation, which is precisely why, months later, when astronomers turned back to the archives, hunting for any trace of 3I Atlas before its official discovery, Rubin's data delivered. It's worth understanding just how long this project has been in the making, because it puts the observatory's precocious accidental discovery in a much bigger context. The idea for what eventually became Rubin Observatory dates all the way back to the mid-1990s, when it was first conceived under a much more modest name, the Dark Matter Telescope, a project aimed at mapping the invisible scaffolding of dark matter that holds galaxies together across the universe. Over the following 3 decades, that original concept grew into something far more ambitious, a facility funded jointly by the National Science Foundation and the Department of Energy, built specifically to conduct the Legacy Survey of Space and Time, a 10-year campaign to photograph the entire visible southern sky, over and over again, building up what will eventually become the single most detailed motion picture ever made of the changing universe. The telescope itself was eventually named after Vera Rubin, the astronomer whose painstaking observations of galaxy rotation in the 1970s provided some of the first definitive evidence that dark matter exists at all, a fitting namesake for an instrument built to hunt for exactly the kind of invisible, hard-to-detect phenomena she spent her career chasing. The scientific goals behind Rubin Observatory extend far beyond hunting for interstellar objects, and it's worth appreciating the scale of ambition here, because it explains why the telescope is quite this powerful. Astronomers are hoping the survey will help resolve some of the deepest open questions in modern physics: the true nature of dark energy, the mysterious force apparently accelerating the expansion of the universe, and the distribution of dark matter itself, mapped out across billions of galaxies with a level of precision no previous survey has come close to achieving. Rubin has already begun contributing to that broader mission, producing what researchers have described as one of the most comprehensive three-dimensional maps of the universe ever created, built from early survey data collected during its opening months of operation. Alongside that cosmological work, the telescope is expected to be exceptionally well positioned to catch rare, fleeting astronomical events that other surveys simply miss: failed supernovas, in which a massive star seems to just vanish without the expected explosive flash, and fast radio bursts, along with a huge range of other transient phenomena that only reveal themselves for a brief moment before fading from view. Interstellar objects, it turns out, are simply one more entry on that very long list of things this telescope was built to catch, just one that happens to be getting an enormous amount of public attention right now, thanks to 3i Atlas. But finding those images wasn't as simple as just pulling up a folder and scrolling through. Rubin's automated pipeline for identifying and tracking fast-moving solar system objects wasn't even operational yet during the commissioning period. The software specifically designed to flag things like asteroids and comets zipping across the frame hadn't been switched on. So Chandler's team had to build custom analysis techniques essentially from scratch, manually combing through the commissioning images, extracting astrometric measurements, precise position data, along with photometry, which is essentially a measurement of brightness over time in order to properly characterize what they'd found. Despite the challenges, the results were remarkable. Using this recovered data, the team was able to independently determine 3i Atlas's orbit, study the structure of its nucleus, and, most impressively, capture the earliest high-resolution evidence yet of the comet's activity, clearly showing the presence of its fuzzy coma, the cloud of gas and dust that surrounds an active comet's icy core, in images taken well before any other observatory on Earth had turned its attention toward the object, which raises an almost bittersweet question that the researchers themselves acknowledged. If Rubin's science validation survey had simply started a little bit sooner, and if its automated detection pipeline had already been up and running, this brand new, barely finished observatory might have been the very first telescope in human history to officially discover 3i Atlas. Not the Atlas survey network it was named after, not any of the other observatories that scrambled to observe it after the fact, but Rubin itself, almost by pure coincidence, simply because it happened to be testing its instruments on precisely the right patch of sky during precisely the right 10-day window. Astronomers joked, somewhat affectionately, that they'd be grumbling about hosting a nearly year-long visit from an interstellar guest, but in truth, the scientific community has been thrilled. 3i Atlas turned into one of the most thoroughly observed objects in the history of solar system astronomy, and Rubin's accidental recovery images added an entirely new, unexpected layer to that story. Proof that the most powerful new eye ever pointed at the sky had, in a sense, already been watching before we even knew there was something worth watching for. The 3i Atlas precovery wasn't the only headline-grabbing discovery to come out of Rubin's commissioning and early survey period either, and it's worth pausing on a couple of the others, because together they paint a picture of just how relentlessly productive this telescope has already been, even before its main 10-year survey truly hit its stride. In January of 2026, a team led by University of Washington astronomers, sifting through early Rubin data, identified an asteroid roughly 0.4 of a mile across that turned out to be the fastest spinning asteroid of its size ever recorded, completing a full rotation in under 2 minutes. A rock roughly the size of 8 football fields, tumbling through space so quickly it would tear itself apart if it were spinning even a little faster. That discovery, published as the first peer-reviewed paper to use data from Rubin's LSST camera, was itself found almost by accident, buried inside pre-survey observations, never originally intended to hunt for anything so specific. And in the observatory's very first weeks of operation, during what astronomers called an early optimization survey, Rubin had already logged more than 11,000 never-before-seen asteroids, including 33 near-Earth objects and 380 trans-Neptunian objects drifting in the frozen outer reaches of the solar system, all discovered in roughly a month and a half of observing. Set against that backdrop, the retroactive discovery of 3i Atlas in the archives almost feels less like an isolated fluke and more like a preview of the telescope's baseline operating mode. Astonishing discoveries showing up practically every time anyone bothers to look closely at the data. Now here's where the story gets even more interesting, because this episode wasn't really about one lucky coincidence. It was a preview of exactly what Rubin Observatory was built to do on a scale that's about to become almost impossible to comprehend. Found would become 4I Rubin. The one after that, 5I Rubin. And so on, potentially for years as Rubin's survey continues finding these objects at a scale nobody has ever previously achieved. It's worth pausing here to be clear about what this actually is, and what it isn't. Nobody has detected 4I Rubin. No such object exists yet, as far as any astronomer on the planet currently knows. This is a placeholder name, a piece of forward planning coined by a scientist who wants the space industry and funding agencies to start thinking now about how to respond. The moment Rubin's alert system does eventually flag a genuine new interstellar visitor, rather than scrambling reactively the way astronomers had to with 3I Atlas, chasing a moving target with instruments that happen to already exist, rather than ones purpose-built for the job. Loeb's argument is essentially that we know, with near certainty, that more of these objects are coming, and coming soon, given Rubin's expected detection rate. So the only real question is whether humanity will be ready with something better than a passive telescope the next time one appears. The mission concept Loeb outlined isn't a slow, gentle rendezvous like the kind used to study asteroids and comets that actually belong to our solar system. Given how fast these interstellar visitors move, and how little advance warning we typically get before they either arrive or depart, Loeb's proposal envisions something closer to a deliberate high-speed impact. A spacecraft launched on a collision course, positioned to snap close-up photographs in the final moments before crashing directly into the object's surface, essentially sacrificing itself for a handful of priceless images and data points gathered in the instant before impact. He suggested that such a mission could also carry instruments capable of sampling the composition of the gas and dust plume surrounding the object as the spacecraft closes in, potentially detecting the building blocks of biology itself. Organic molecules, or in the most tantalizing scenario, some kind of biological signature. Even if the object itself ultimately turns out to be nothing more than an ancient frozen iceberg drifting between the stars. Loeb has been careful to frame this as pure exploration, a way of turning what would otherwise be a fleeting, frustrating glimpse of an object we can never send a slow, careful mission toward into a genuine, if brief and destructive, close encounter. This kind of high-speed, kamikaze-style encounter has precedent in a sense, even if nothing quite like it has ever been attempted on an object moving this fast, or arriving with this little advance notice. NASA's DART mission, which deliberately crashed a spacecraft into an asteroid moonlet back in 2022 to test humanity's ability to deflect a potentially hazardous object, proved that a targeted, high-velocity impact mission is technically achievable, and that useful science, it can be extracted right up to and including the moment of destruction. But DART had years of planning, a well-characterized target moving on a slow, predictable, thoroughly mapped orbit within our own solar system. An interceptor built to catch an object like a future 4I Rubin would have none of those luxuries. It would need to be built, tested, and essentially sitting ready on a launch pad, or already parked in a waiting orbit, well before the target is even discovered, because the entire window between detection and the object's closest approach might only last a matter of weeks or months. The technical challenge here is brutal and worth sitting with for a moment, because it explains why nothing like this has ever actually been attempted. Launching an interceptor on a collision course with a future interstellar object, something Loeb has referred to by the placeholder name 4I/Rubin, would require detecting that object while it's still relatively far away, somewhere between 5 and 10 astronomical units from the Sun, and then reacting fast enough to get a spacecraft launched on the correct trajectory before the object sweeps past and heads back out into the galaxy for good. There's essentially no room for delay. By the time an object like 3I Atlas gets close enough to observe in real detail, it's often already too late to meaningfully change a spacecraft's trajectory to intercept it, which is exactly why every observation of 3I Atlas made by every telescope on Earth and in space has been a passive one, watching from a distance, never touching, never sampling directly. There are already 2 mission concepts floating around in the space community that are relevant here, and researchers have actually run the numbers on how well they'd perform against the kinds of targets Rubin is expected to find. One is called Comet Interceptor, a mission with fairly limited ability to change its velocity once launched, essentially designed to wait in a parked orbit and only react to targets that happen to pass through a narrow, favorable trajectory window. Researchers estimate the odds that Rubin's survey will actually produce an interstellar object reachable by Comet Interceptor, given its limited maneuverability, sit at somewhere around a mere 0.07%, vanishingly small. The second concept, a more capable but still hypothetical mission called Bridge, hasn't even been formally approved yet, but if it were built, researchers estimate Rubin's survey could plausibly deliver somewhere between 3 and 7 reachable interstellar targets over the full run of the mission. Still an extraordinarily narrow window, but genuinely non-zero, and enough to make serious scientists take the idea of an interceptor mission seriously as something worth actually funding and building, rather than dismissing as science fiction. What all of this adds up to is a fundamental shift in how humanity is about to relate to these objects. For the entirety of recorded history up until just the last few years, an interstellar visitor passing through our solar system was treated as an almost mythical, once-in-a-generation event, something scientists scrambled to observe for a few desperate weeks before it vanished, using whatever telescopes happened to be available at the time, with essentially no chance of ever preparing in advance. Rubin Observatory is on track to make that experience routine. Not boring, not less scientifically valuable, but routine in the sense that instead of waiting years or decades between sightings, astronomers may soon be tracking multiple interstellar objects simultaneously, cataloging their trajectories, chemistries, and structures with a level of statistical rigor that's simply never been possible before, precisely because there's never been a large enough sample size to study. And that changes the entire nature of the question everyone keeps asking about objects like 3I Atlas. Right now, with only 3 confirmed interstellar visitors ever detected, it's almost impossible to say with any real statistical confidence what's normal and what's unusual for an object arriving from another star system. Every anomaly noted in 3I Atlas's behavior, its size, its trajectory alignment, its unusual water chemistry, its faint X-ray glow, has to be evaluated against a sample size of essentially 2 prior objects, Oumuamua and Borisov, both of which behaved quite differently from each other and from 3I Atlas in their own right. Once Rubin starts flagging dozens or hundreds of these objects, astronomers will finally have something they've never had before, a real population to study, a genuine baseline of what interstellar comets and asteroids typically look like, how they typically move, what they're typically made of. Suddenly, questions like whether 3I Atlas's trajectory alignment with the ecliptic plane was genuinely improbable, or whether its size was truly unusual, will have actual statistical answers instead of educated guesses drawn from a sample of 3. There's something almost poetic about the fact that the observatory poised to deliver that answer had already, quietly, unknowingly, photographed the very object that sparked the entire debate, days before anyone else on the planet even knew to look. Rubin didn't set out to discover 3I Atlas. It wasn't hunting for interstellar objects at all during those commissioning nights in late June of 2025. It was simply testing its systems, calibrating its enormous camera, making sure everything worked as designed before its real mission even began. And in the middle of that routine checklist, it captured, by pure accident, 9 separate images of a visitor from another star system that nobody on Earth had noticed yet. That's the thing about a telescope this powerful, this sensitive, and this wide-reaching. It doesn't just find what you tell it to look for. It finds things nobody was looking for at all, simply because it's watching more of the sky, more often, in more detail, than anything humanity has ever built before. Somewhere in Rubin's ongoing torrent of nightly images, the 800,000 alerts from a single test night, the eventual 7 million alerts per night once the survey reaches full speed, the signature of the next interstellar visitor is probably already sitting there, or will be soon, waiting for the automated pipeline, now fully operational, to flag it in real time. The instant its velocity crosses that 42 km per second threshold and gives away exactly what it is. The next Oumuamua, the next Borisov, the next 3I Atlas might not take astronomers months to identify after the fact anymore. It might not require a network of scattered telescopes scrambling to catch a fleeting glimpse before the object disappears. It might simply appear as a single line in an automated alert delivered to observatories around the world within minutes of being captured, flagged by an algorithm trained specifically to recognize the unmistakable signature of something that came from somewhere else entirely. And if Avi Loeb and researchers pursuing missions like Bridge ever get their wish, that alert might not just mean another few months of passive telescope observations from a comfortable distance. It might mean a spacecraft already sitting in a parking orbit somewhere, waiting, ready to launch on short notice, racing to catch up with an object, moving fast enough to escape the sun's gravity entirely, hoping for just a few seconds of close-up photography and direct sampling before the impact that ends the mission. Humanity's first real physical encounter with material from another star system, rather than just another set of numbers and spectra gathered from millions of miles away. We are, quite possibly, standing right at the edge of that shift. Rubin Observatory's legacy survey of space and time has only just formally begun, its full 10-year run barely underway, and it has already rewritten the record books for asteroid discoveries, delivered unprecedented deep field images of distant galaxies, and, almost as an afterthought during its testing phase, quietly beaten every other telescope on the planet to a visitor from another star. If the early estimates hold up even remotely close to accurate, the era of interstellar objects being rare, mysterious, almost mythical events is ending. What comes next is a survey that watches nearly the entire visible sky, night after night, for a full decade, cataloging everything that moves, everything that changes, everything that doesn't belong,